A guard paces his patrol route, back and forth, never seeing you. Then you step into the light, and he turns, chases, and attacks. How does he know to do all of that, in the right order? Not a giant pile of if statements. A behavior tree, the little brain that decides what the AI does next. Watch this tree tick, frame by frame, and watch the guard react. One quick, honest note before we start. Everything here is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and data structures, visually explained. 23 of them, each a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us go meet the tree. Here is the trap people fall into. You write the guard as a wall of if statements. If the player is visible, chase. Else if in range, attack. Otherwise, patrol. It works, for about 5 minutes. Then you add fleeing, and searching, and taking cover. The conditions tangle together. One new rule quietly breaks 3 others. A behavior tree fixes this. It is a tree of small, reusable nodes that the AI runs, top to bottom, every single frame. The tree answers exactly one question: what should I do right now? Let us build one, node by node. A behavior tree is made of nodes, and there are 2 families of them. The leaves do the real work. Actions, patrol, chase, attack, move. And conditions, is the player visible, am I in attack range? Leaves sit at the bottom of the tree. Here is the rule that ties it all together. Every node, when it runs, when it ticks, returns exactly one of 3 statuses. Success, if it finished. Failure, if it could not. Or running, if it is still working, mid-action, across many frames. That running status is what lets a long action, like walking a route, span frame after frame. Hold on to those 3 words. Above the leaves sit the composite nodes, the branches that combine their children. There are 2 you must know. First, the sequence, often drawn as an arrow. It runs its children left to right. The moment one child fails, the whole sequence fails and stops. It succeeds only if every child succeeds. Think of it as an, do all of these, in order. Second, the selector, often drawn as a question mark. Also left to right, but flipped. The moment one child succeeds, the selector succeeds and stops. It fails only if every child fails. That is, or, try these until one works. And if any child returns running, its parent returns running too, and stops right there for this frame. Now the guard's actual brain. The root is a selector. Its 2 children, in priority order, are a sequence, then patrol. The sequence holds 4 leaves, in order, is the player visible, chase, in attack range, attack. Every frame, we tick from the root. Watch scenario 1, where the player is hidden. The selector ticks its first child, the sequence. The sequence ticks its first leaf, is the player visible? Failure. So the sequence fails at once, and never touches chase or attack. The selector's first child failed, so it falls through to its second child, patrol. Patrol returns running. The guard patrols. Green is success, red is failure, yellow is running. Now scenario 2, you step into view. Is the player visible? Success. The next leaf, chase, returns running, because he is moving toward you. A running child makes the sequence running, and it stops there. The selector sees running, and returns running. The guard chases. Scenario 3, he reaches you. Visible, success. Chase, success, he has arrived. In attack range. Success. Attack returns running. The guard attacks. Same tree, ticked the same way, every frame. Only the world changed, and the behavior followed. Why a tree, and not a state machine? Both can drive this guard. A finite state machine is states plus transitions, patrol, chase, attack, with arrows between them. With 3 states, it is fine. But every new state has to wire transitions to and from the others. 10 states can need dozens of arrows. It becomes a spaghetti of transitions. A behavior tree scales cleanly instead. You add a behavior by dropping in a new subtree. Priorities are just left to right order, no rewiring. And running lets long actions span frames for free. That modularity is why behavior trees drive the enemy AI in countless shipped games. When you need to add one more behavior at 3 in the morning, the tree forgives you. Here it is in real code, and it is shorter than you would expect. A sequence ticks each child and returns on the first status that is not success, the first failure or running. If it gets through them all, it returns success. A selector is the mirror image. It returns on the first status that is not failure, the first success or running. If they all fail, it returns failure. A leaf simply runs its function and reports success, failure, or running. Then the whole guard is one selector wrapping a sequence and a patrol leaf. You tick the root once per frame. That is a behavior tree, end to end. Let us lock it in. A behavior tree decides what an AI does next, tick from the root every frame. Leaves are actions and conditions. Every node returns success, failure, or running. A sequence is an, it fails on the first failure, and succeeds only if all succeed. A selector is or, it succeeds on the first success, and fails only if all fail. Running lets a long action span frames, and each status flows back up to the root. Put a sequence under a selector, order the children by priority, and a guard patrols, chases, and attacks, with no tangle of if statements. So that is the behavior tree, the decision-making brain that sits on top of your pathfinding. Your AI can now find a path, and decide what to do with it. But a behavior tree only reacts to the world as it is right now. So how does an AI plan ahead, look into the future and outplay you at chess or tic-tac-toe? That is Minimax, the algorithm that searches moves before it makes one. It is the next video. If you want the whole picture, 23 algorithms, each a diagram and clean Python, my book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.